Space is like the final frontier, a massive playground of endless mysteries that have fascinated humans for centuries. From the echoing symphony of cosmic sounds to the dawn of time itself, join us on a journey as we unravel the secrets of the universe and speculate about what lies ahead. Together, we'll push the boundaries of our cosmic knowledge and look at what exists outside of our universe. The observable universe is a concept that stretches the limits of our imagination and scientific understanding. It is defined by the furthest reaches of the cosmos that we can, in principle, observe from Earth, not just with our naked eye, but with the most advanced telescopes ever created. At the heart of this definition lies the speed of light, a constant that travels at about 300,000 kilometers per second. Light from a star far away takes time to reach us, and since the universe is about 13.8 billion years old, this means we can only see as far away as the light has had time to travel since the universe's inception. This sets our cosmic horizon at approximately 93 billion light-years in diameter, even though the universe itself may be infinitely larger or part of a much grander multiverse. In essence, the observable universe includes every galaxy, star, planet, and particle that has had enough time to send light signals to our little corner of the cosmos, revealing a universe teeming with mysteries waiting to be uncovered. Measuring the size of the observable universe is an intricate process that combines observation, mathematics, and a profound understanding of cosmic expansion. At its core, scientists rely on the study of light from the furthest reaches of space. By observing the redshift of light, a phenomenon where light stretches into longer, redder wavelengths as it travels across the expanding universe, astronomers can determine how fast an object is moving away from us and, by extension, its distance. Another pivotal tool is the cosmic microwave background radiation, a relic heat from the Big Bang, providing a snapshot of the early universe. By measuring the tiny fluctuations in this radiation's temperature, scientists can infer the universe's age and expansion rate, using these to calculate the radius of the observable universe. This task requires precise instruments, such as the Hubble Space Telescope and the European Space Agency's Planck satellite, which offer a glimpse into the universe's farthest corners. Through these methods, the observable universe's size is determined to be about 46.5 billion light-years in radius, a measure that encapsulates the vastness of the cosmos as we can see it. Within the vast expanse of the observable universe lies a cosmic tapestry of celestial objects, each playing a unique role in the grand scheme of the cosmos. Stars, the fundamental building blocks of galaxies, illuminate the universe, ranging from tiny, dim red dwarfs to massive, bright blue supergiants. Planets, diverse in size and composition, orbit these stars, with some harboring the potential for life as we know it. Galaxies, immense assemblages of stars, dust, and dark matter, come in various shapes and sizes, from the majestic spirals like our own Milky Way to the vast ellipticals containing trillions of stars. Nebulae, vast clouds of gas and dust, serve as stellar nurseries where new stars are born. Pulsars and quasars emit powerful beams of radiation, acting as cosmic lighthouses, while black holes, regions of space with gravitational pull so strong that not even light can escape, lurk at the centers of many galaxies. Each of these celestial objects contributes to the intricate web of the cosmos, offering clues to the universe's birth, evolution, and eventual fate. The concept of the observable universe has undergone a profound transformation, propelled by leaps in technology and scientific insight. In the past, our understanding was confined to what could be seen with the naked eye, limiting our view to the stars and planets within our own Milky Way. The invention of the telescope in the early 17th century marked the beginning of a new era, expanding our vision and unveiling the vastness of the universe. As telescopes grew more powerful, astronomers discovered galaxies beyond our own, pushing the boundaries of the known universe further. The 20th century brought even more significant advancements. With the launch of space-based telescopes like the Hubble Space Telescope, astronomers could peer deeper into the cosmos, free from the distortive effects of Earth's atmosphere. These eyes in the sky have allowed us to detect objects billions of light years away, observe the cosmic microwave background radiation, and study the universe's expansion, providing empirical evidence that supports the Big Bang theory. In the realm of theoretical physics, concepts like dark matter and dark energy have reshaped our understanding of the universe's composition and its expansion. The advent of digital technology and computer simulations has enabled scientists to model the universe's evolution with unprecedented detail, allowing for predictions and discoveries that push the frontiers of our knowledge. As we stand on the cusp of further advancements, with projects like the James Webb Space Telescope and the Square Kilometre Array, the concept of the observable universe continues to evolve. Each technological leap not only expands the boundaries of our cosmic horizon, but also deepens our understanding of the universe's mysteries, underscoring the intrinsic link between technological progress and our quest to comprehend the cosmos. Despite the considerable strides made in observational technology, we still face significant limitations in our quest to observe the universe. One of the primary challenges is the finite speed of light. While it allows us to look back in time towards the universe's birth, it also means we cannot see beyond a certain horizon. Events or objects that are too far away have not had enough time for their light to reach us. Furthermore, the universe's expansion exacerbates this limit, causing distant galaxies to recede from us faster than the speed of light, pushing them beyond our observational reach. Additionally, our observations are hindered by cosmic dust and gas that absorb and scatter light, obscuring our view of certain objects and events. This is particularly true for observations in the optical spectrum, where dust clouds can completely block the light from stars or galaxies behind them. Another significant limitation comes from our reliance on electromagnetic radiation, light, for most of our observations. While this includes a range of wavelengths from radio waves to gamma rays, there are phenomena in the universe that do not emit light or do so very weakly, making them incredibly difficult to detect. Technological limitations also play a role. Our current telescopes and detectors have limits in sensitivity and resolution, constraining the distance and detail at which we can observe celestial objects. Although instruments continue to improve, there is always a trade-off between the size of the telescope, its location, and the cost of building and operating it. All our observations are constrained by our current understanding of physics and the universe. Theories like dark matter and dark energy suggest that there are significant components of the universe that we cannot observe directly with any existing technology, presenting fundamental challenges to our ability to fully understand the cosmos. As we develop new technologies and theoretical frameworks, some of these limitations may be overcome, But the nature of our observations means we will always grapple with certain constraints in our efforts to observe the universe. The observable universe might seem at first thought to be a perfect sphere centered around us, with its reach extending uniformly in all directions. However, the reality is slightly more nuanced due to the universe's dynamic nature and its expansion over time. The observable universe is not the exact same size in all directions due to slight variations in the universe's expansion rate and the irregular distribution of matter throughout cosmic history. One of the fundamental reasons for this asymmetry lies in the cosmic inflation that occurred fractions of a second after the Big Bang. This rapid expansion could have varied slightly in intensity from one region to another due to quantum fluctuations, affecting the homogeneity of the universe on the largest scales. Additionally, as the universe expands, it does so unevenly because of the gravitational pull of massive structures like galaxy clusters, which can slightly warp the space around them, leading to variations in the observable universe's extent in different directions. Another factor contributing to this variance is our position within the Milky Way galaxy. The galaxy's dense disk of stars and dust can obscure our view of the universe in the plane of the Milky Way, effectively limiting our ability to observe in those directions as clearly as we might in others. This results in certain observational constraints that give us a somewhat anisotropic, not uniformly distributed view of the cosmos. Furthermore, the light from distant objects is affected by the expansion of the universe. The farther away an object is, the more its light has been stretched to longer, redder wavelengths, a phenomenon known as redshift. Advanced cosmic structures observed in one direction might appear younger or older in another, depending on how the universe's expansion rate has affected their light reaching us. While these factors make the observable universe slightly irregular in shape, it's worth noting that on a cosmological scale, these differences are quite minor. The observable universe remains, to the best of our current measurements, remarkably uniform in all directions, a testament to the isotropic principle that underpins modern cosmology. Light and time are inextricably linked in shaping our understanding of the observable universe, weaving a complex tapestry that stretches across the vast emptiness of space to tell the story of the cosmos. The fundamental relationship between them is embedded in the very fabric of the universe, dictating what we can see and how we perceive the history of everything around us. At the heart of this relationship is the concept that light travels at a finite speed, approximately 300,000 kilometers per second. This means when we observe celestial objects, we are seeing them as they were in the past. The light from our sun takes about 8 minutes to reach us, so we see the sun as it was 8 minutes ago. Similarly, when we gaze at a galaxy 5 million light-years away, we are seeing light that left that galaxy 5 million years ago. This time travel aspect of light allows astronomers to look back in time as they observe objects farther away from Earth, providing a window into the early universe. Through this understanding, the observable universe becomes a vast historical archive. The farther out into the cosmos we look, the older the light becomes, offering clues about the early stages of the universe's formation, the birth and death of the first stars, and the assembly of galaxies. This temporal journey reaches its apex with the cosmic microwave background radiation, a faint glow left over from the Big Bang, observed as it was about 13.8 billion years ago, providing a snapshot of the universe in its infancy. However, the finite speed of light also underscores a fundamental limit to our cosmic vision. There exists a horizon beyond which the universe is unobservable to us, not because it doesn't exist, but because the light from these distant regions hasn't had enough time to reach us since the birth of the universe. Thus, the observable universe isn't just a physical space, but a temporal boundary, encompassing all that can be seen within the age of the universe. The intricate concept of the observable universe not only captivates the imagination, but also poses substantial challenges and raises philosophical questions about the nature of existence and reality. As we push the boundaries of what can be observed, we also delve into the philosophical implications of understanding an ever-expanding universe. This pursuit raises the question of whether our perceptions of the universe are shaped by the limitations of our tools and the fundamental laws of physics, or if they reflect a deeper reality. The nature of cosmic observation itself underpins a significant philosophical discourse on observation versus reality. The fact that we are observing the light from celestial bodies as they were, not as they are, suggests that our understanding of the universe is inherently retrospective. This retrospective view challenges the notion of present reality in cosmology and raises questions about the constancy of physical laws over time and space. It beckons us to consider the possibility that parts of the universe might fundamentally differ from what we can observe and understand through current scientific methods. Moreover, the concept of the cosmic horizon, the maximum extent we can observe due to the finite speed of light, introduces the philosophical concept of unknowable truths. Beyond this horizon lie aspects of the universe about which we might never glean information, suggesting that our understanding of the cosmos is limited not just technically, but also conceptually. This limitation resonates with the philosophical exploration of the limits of human knowledge and the potential existence of unknowable truths. From a methodological perspective, the study of the observable universe challenges the empirical foundation upon which modern science is built. If empirical evidence is unattainable for phenomena beyond the cosmic horizon, can these phenomena still be considered within the purview of scientific inquiry? This question is crucial for the philosophy of science as it explores the definitions of what can be scientifically known. The observable universe also dramatically illustrates the concept of cosmic solitude, where the vastness of the universe, coupled with the finite speed of light, might imply that significant portions of the universe are forever isolated from each other. This notion can be paralleled with philosophical existentialism, which often contemplates the solitude and isolation of human existence. Just as we might never interact with or understand regions beyond the cosmic horizon, so too might individuals feel a profound isolation despite being surrounded by others. The expansion of the universe and the acceleration driven by dark energy touch upon philosophical discussions about the future and fate of the cosmos. The potential for a continually expanding universe that grows colder and emptier poses existential questions about the end of everything. Philosophical inquiries into the meaning of a universe headed towards heat death, where stars fade and galaxies recede into oblivion, reflect on the broader implications for meaning and purpose in the face of cosmic decline. The relationship between light and time is central to cosmology, offering a bridge to the past and allowing us to reconstruct the history of the cosmos while highlighting the limits of our observational reach. Through it, we grasp both the vastness and the age of the universe, making it a fundamental component of our quest to understand our place in the cosmos. The intriguing question of what lies beyond the observable universe has fueled various theories and speculations within the scientific community, stretching the boundaries of our understanding and imagination. Given that the observable universe is defined by the furthest distance from which light has had enough time to reach us, it naturally prompts curiosity about what exists beyond that cosmic horizon. One prevalent theory suggests that the universe is much larger, possibly infinite, extending far beyond the observable limits. This idea is supported by models of cosmic inflation, which propose a period of rapid expansion immediately after the Big Bang. According to this model, the universe expanded exponentially within a fraction of a second, suggesting that the space beyond our observational reach is simply more of the same, more galaxies, stars, and planets, potentially hosting an untold number of civilizations. Another theory posits the existence of a multiverse, a concept that proposes our universe is just one of many universes, each with its own physical laws and constants. This theory arises from various domains, including the interpretations of quantum mechanics and the mathematical solutions of string theory. In this view, the space beyond the observable universe might contain entirely different universes, with properties and laws of physics that could vary drastically from our own. Cosmologists also consider the possibility of a finite but unbounded universe, akin to the surface of a sphere. In this model, if you could travel far enough in one direction, you might eventually return to your starting point, suggesting that the universe loops back on itself. This theory implies that the space beyond the observable universe is simply more of the universe that we cannot see due to the limitations imposed by the speed of light and the age of the universe. Additionally, some theories suggest varying degrees of homogeneity and isotropy. While the observable universe appears relatively uniform on large scales, it's conceivable that the universe's structure and distribution of matter might change beyond our cosmic horizon, presenting a landscape that could challenge our current understanding of cosmology. While these theories are deeply fascinating, they remain speculative and are constrained by our current technological capabilities and understanding of physics. Until we can observe or measure phenomena that offer direct insights into the space beyond the observable universe, these theories will continue to stir both scientific inquiry and imagination. Scientists use mathematical models as a fundamental tool to predict and theorize about the nature of the cosmos beyond the observable universe, venturing into realms that lie far beyond our current observational capabilities. These models are grounded in the laws of physics, as we understand them, extrapolated to apply to the vast, unseen stretches of the universe. One crucial aspect of this extrapolation lies in the theory of cosmic inflation, which suggests that the universe underwent a rapid expansion immediately after the Big Bang. The mathematical models of inflation, rooted in quantum field theory and general relativity, imply that the universe could be infinitely larger than the observable portion, containing structures and phenomena too far away for their light to have reached us. Another area where mathematical models play a pivotal role is in the study of the cosmic microwave background, CMB, radiation. By analyzing slight temperature fluctuations in the CMB, scientists use statistical models to understand the early universe's density fluctuations. These fluctuations are thought to be the seeds of all current cosmic structures, and by modeling how they evolve over time, scientists can infer the large-scale structure of the entire universe, not just the part we can see. String theory and other theories of quantum gravity also provide mathematical frameworks that suggest the existence of additional dimensions in the multiverse. These models, though highly speculative, open the possibility of multiple universes with different laws of physics. Scientists use complex mathematics to predict how these universes might arise and interact, potentially offering explanations for phenomena that remain mysterious within our own universe. Moreover, simulations play a critical role in modern cosmology, with scientists using sophisticated computer models to simulate the evolution of the universe under different conditions. These simulations incorporate the laws of physics and cosmological principles to predict the distribution of galaxies, the nature of dark matter and dark energy, and even the fate of the universe. By tweaking these models, scientists can explore a wide range of outcomes and scenarios that might exist beyond the observable universe. Through the application of mathematical models, grounded in the fundamental laws of physics and enhanced by computational simulations, scientists can extrapolate the principles observed within our cosmic neighborhood to make educated predictions about the nature of the universe at its grandest scales. While these predictions remain to be tested against empirical evidence, they offer a fascinating glimpse into the potential realities that lie beyond our direct observation, pushing the frontiers of our cosmic understanding. The possibility of other universes existing beyond our own is a tantalizing question that resides at the frontier of modern cosmology and theoretical physics, often discussed under the framework of the multiverse theory. While definitive empirical evidence for the existence of other universes remains elusive due to the inherent limitations of observing beyond the observable universe, several theoretical models suggest that multiple universes could indeed exist. One such model arises from the concept of cosmic inflation, a rapid expansion following the Big Bang. Inflationary theory, supported by observations of the cosmic microwave background radiation, suggests that if inflation is possible in one region of space, it could occur in others. This scenario could lead to pocket universes within a larger, possibly infinite multiverse, each with its own physical constants and laws. String theory, a candidate for the theory of everything, also provides a framework for the existence of a multiverse. It posits that the fundamental building blocks of the universe are not point particles, but tiny vibrating strings. The different modes of these strings' vibrations could correspond to different particles and forces, leading to a vast landscape of possible universes, each with its unique configuration of the laws of physics. Another perspective comes from the many worlds interpretation of quantum mechanics, which suggests that every quantum event spawns a new universe for each possible outcome, leading to an ever-branching tree of realities. Though these ideas offer intriguing possibilities, it is important to approach them with scientific skepticism. The concept of other universes stretches the limits of current scientific methodology, as any universe beyond our own observable realm is, by definition, beyond the reach of direct observation and experimentation. Consequently, Debates continue over whether the multiverse theory can be considered a scientific hypothesis or philosophical speculation. Ultimately, while the existence of other universes remains a speculative venture at present, it pushes the boundaries of our understanding and challenges us to consider the cosmos in its most grand and mysterious form. Advances in theoretical physics, observational cosmology, and perhaps new frameworks of understanding might one day provide clearer insights into this profound question. Dark matter, an enigmatic substance that does not emit, absorb, or reflect light, and is detectable only through its gravitational effects, plays a pivotal role in theories about the universe, extending well beyond the observable limits. Accounting for approximately 85% of the total matter in the universe, its presence is inferred from the gravitational influence it exerts on visible matter, such as the rotational speeds of galaxies, which would not be possible based on visible matter alone. In the context of the universe beyond the observable limits, dark matter is theorized to be a critical component in the formation and structure of the cosmos. It acts as a cosmic scaffolding around which visible matter congregates, guiding the formation of galaxies and large-scale structures from the very earliest times. The distribution and density of dark matter in the universe influence the web-like structure observed in the large-scale distribution of galaxies, suggesting a universe that is homogeneous and isotropic on the largest scales, but intricately structured and clumpy on smaller scales. Furthermore, dark matter is central to models of cosmic inflation and the expansion of the universe. Inflationary theory posits that quantum fluctuations in the early universe, magnified by inflation, laid down the seeds for the distribution of dark matter, which in turn influenced the formation of cosmic structures. This underlying dark matter framework extends beyond the observable universe, implying that the processes and structures we observe may be replicated on an even grander scale in the parts of the cosmos we cannot see. The nature of dark matter also has implications for theories about the universe's ultimate fate and its broader architecture, including the possibility of other universes. If dark matter interacts through forces other than gravity, as some theories suggest, it could open up novel pathways to understanding the cosmos's structure and the fundamental laws that govern it. Despite the central role dark matter plays in these theories, it remains one of the universe's greatest mysteries, with its exact nature and properties yet to be determined. Efforts to detect dark matter directly through experiments deep underground or in space, and to understand its role in the larger cosmic puzzle, continue to push the boundaries of our knowledge of the universe, stretching beyond the limits of what we can observe. The concept of the multiverse presents a profound challenge to our traditional understanding of space, urging us to rethink the very fabric of reality and the parameters that define our universe. Traditionally, space has been viewed as a continuous expanse that houses all matter and energy, extending infinitely or wrapping around itself in a finite but boundless manner. The universe within this framework is considered to be all there is, the ultimate stage for the drama of physics and cosmology. The introduction of the multiverse theory adds layers of complexity to this view, suggesting that what we perceive as the universe may be just one of countless other universes, each with its own expanse of space, laws of physics, and possibly even different dimensions. This leads us to reconsider space not as a uniform, singular entity, but as a component of a much larger, possibly infinite tapestry of realms that lie beyond our current perceptual and conceptual reach. One of the key challenges posed by the multiverse concept is the notion of space being quantized or discrete at scales beyond our universe. If different universes in the multiverse have their own separate expanses of space, it implies boundaries or transitions between these realms, an idea that fundamentally clashes with the smooth, continuous nature of space as described by general relativity. Moreover, the theory extends the idea of cosmic inflation, suggesting that bubbles of space-time could continuously form and give rise to new universes. This challenges our understanding by implying that space is not merely a passive backdrop, but an active, generative part of the cosmos, capable of spawning entirely new universes with potentially unique properties. The multiverse also challenges our comprehension of the cosmological principle, the idea that, on a large scale, the universe is homogeneous and isotropic, looking the same in all directions. If our universe is but one bubble in a frothy sea of other universes, the uniformity and isotropy we observe might not hold beyond our cosmic horizon, suggesting a heterogeneity to the broader multiverse that defies our current cosmological models. The concept of what lies beyond the observable universe continues to challenge our understanding and philosophical assumptions about the nature of reality and the universe itself. As we speculate on the vastness that extends past the cosmic horizon, we are drawn into deep reflections on the nature of existence and the structure of the universe. The idea that the universe might be infinite, with an endless sea of galaxies, stars, and potentially civilizations, invites us to reconsider our place within it. Such a perspective not only humbles our understanding but also expands it, suggesting a universe where possibilities are limitless and where the principles of physics as we understand them may only apply locally. This infinite expanse could imply a universe where the constants and laws we consider universal are merely regional bylaws, varying significantly across different expanses of the cosmos. On the other hand, the multiverse theory presents a radical shift in conceptualizing reality. If our universe is just one of many, each with its own set of physical laws and constants, the philosophical implications are profound. This scenario challenges the very idea of a unified physical law and suggests that our understanding of nature might be fundamentally incomplete. Philosophically, this can be seen as an extension of modal realism in philosophy, where all possible worlds are as real as the observable universe, but with each world following potentially different paths and principles. Moreover, the concept of a finite but unbounded universe, akin to the surface of a sphere, touches on ancient philosophical inquiries about the infinite versus the bounded. It rekindles age-old debates on whether the universe has a boundary and what beyond might mean in such a context. This notion complicates our understanding of space and infinity, suggesting that our universe might loop back on itself in a higher dimensional space, making the cosmos a more intricately connected and cyclic entity than previously thought. Additionally, the discussion of homogeneity and isotropy beyond the observable limits invites a re-evaluation of the cosmological principle, the assumption that the universe is uniform and isotropic on large scales. If the universe's structure changes beyond what we can see, it might suggest that our local observations are just a small, perhaps not entirely representative sample of a much more diverse cosmic tapestry. This idea challenges the reductionist view of the universe and supports a more holistic, possibly fractal perspective on cosmology. These speculations not only broaden our conceptual horizons, but also imbue our scientific pursuits with a philosophical depth that questions the very foundations of knowledge and reality. They encourage a shift from a potentially arrogant anthropocentrism to a more humble acknowledgement of our limited place within a possibly infinite and fundamentally unknowable cosmos. As we continue to push the boundaries of both technology and theory, our understanding of what lies beyond the observable universe will likely evolve, continuously shaping and reshaping the philosophical foundations of cosmology. These explorations not only redefine our conception of the universe, but also, ultimately, of the self and our place within this vast cosmic context. This ongoing dialogue between observation, theory, and philosophy highlights the profound depth of our quest to understand the universe and our place within it. As speculative as these theories are, they serve as a critical reminder of the vastness of the unknown and the potential limits of human understanding, urging us always to look deeper and question more fundamentally. Grasping the full implications of the multiverse on our understanding of space requires a fundamental shift in perspective, pushing the boundaries of current physics and entering realms that intertwine science with philosophy. While these concepts stretch our imagination and challenge our foundational views, they also underscore the beauty and mystery of scientific inquiry, leading us to explore questions that probe the very nature of reality itself. The Big Bang Theory stands as the cornerstone of modern cosmology, offering a compelling and widely supported explanation for the origin and evolution of the universe. Contrary to what the name might imply, the Big Bang was not an explosion in space, but rather an expansion of space itself. According to the theory, the universe began in an extremely hot and dense state about 13.8 billion years ago and has been expanding ever since. This theory is bolstered by a multitude of observational evidence. One of the most pivotal pieces is the discovery of the cosmic microwave background radiation, CMB, a faint glow that fills the universe, detected in every direction with a remarkably uniform temperature. This radiation is the afterglow of the Big Bang, cooled to microwave frequencies by the universe's expansion, and it provides a snapshot of the infant universe about 380,000 years after its inception, at the moment when atoms first formed and the universe became transparent to radiation. Another crucial line of evidence comes from the observation of galaxies moving away from us in all directions, implying that the universe is expanding uniformly. This observation is often described through Hubble's law, which states that galaxies are receding from each other at speeds proportional to their distances. This expansion suggests that, if we trace the universe's history backward in time, it would converge to a state of infinite density and temperature, a singularity from which the Big Bang expansion began. Additionally, the theory accurately predicts the abundance of the light elements hydrogen and helium in the universe, formed in the first few minutes after the Big Bang in a process known as Big Bang nucleosynthesis. The precise ratios of these elements observed in the universe match the predictions of the theory, providing further support. The Big Bang theory not only describes the beginning of the universe, but also sets the stage for the formation of all cosmic structures, from galaxies to stars to planets. It provides a framework for understanding the universe's evolution and the physical processes that have shaped it. Despite its success, the theory leaves unanswered questions, such as the precise nature of the singularity, the cause of the Big Bang, and what, if anything, preceded it. These questions continue to fuel astronomical research and theoretical physics, pushing the boundaries of our understanding of the cosmos. Cosmic microwave background, CMB radiation maps, serve as a window into the early universe, offering us a profound insight into its infancy. The CMB is the afterglow of the Big Bang, a faint cosmic whisper that fills the universe, originating from a time approximately 380,000 years post-Big Bang, when photons were first able to travel unimpeded as the universe cooled and became transparent. Mapping the CMB provides a snapshot of the universe at this pivotal moment, allowing scientists to decipher the initial conditions that led to the formation of galaxies, stars, and other cosmic structures. One of the most remarkable aspects of the CMB is the uniformity of its temperature, around 2.7 Kelvin, 270.45 degrees Celsius, minus 454.81 degrees Fahrenheit, with tiny temperature fluctuations on the order of microkelvins. These minuscule variations in density and temperature are of profound importance. They represent the seeds of all future structure. The denser regions eventually gravitated together to form galaxies and clusters of galaxies. By studying these fluctuations, scientists can test theories of cosmic inflation, the rapid expansion of the universe that is thought to have occurred fractions of a second after the Big Bang, smoothing out and stretching the universe, but leaving behind these small density fluctuations. CMB maps also provide a critical test for our understanding of the content and geometry of the universe. The patterns of the fluctuations can be used to measure the universe's overall curvature, determining whether the geometry of space is flat, open, or closed. Observations have shown that the universe is remarkably flat, a key prediction of inflationary theory. Moreover, these maps have allowed cosmologists to accurately determine the universe's age and its composition, including the proportions of dark matter, dark energy, and normal matter. The precision measurements of the CMB from missions like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite have led to the establishment of the Lambda Cold Dark Matter, LCDM model, as the standard model of cosmology, which describes a universe that is approximately 13.8 billion years old, with about 5% ordinary matter, 27% dark matter, and 68% dark energy. In essence, cosmic microwave background radiation maps are akin to cosmic archaeology, uncovering the earliest observable period in the universe's history. They allow scientists to refine our models of the universe's birth, evolution, and current state, providing invaluable insights into fundamental physics and cosmology. One of the most compelling pieces of evidence supporting the Big Bang theory is the discovery of the cosmic microwave background radiation, CMBR. In the middle of the 20th century, two American radio astronomers, Arno Penzias and Robert Wilson, stumbled upon this faint background noise while experimenting with a microwave antenna. This discovery, which earned them a Nobel Prize, offered a glimpse into the universe's infancy. approximately 13 billion years ago. The CMBR is essentially the afterglow of the Big Bang, stretched and cooled over billions of years as the universe expanded. Additionally, the Hubble's law, named after Edwin Hubble, further bolsters the Big Bang theory. Hubble observed that galaxies are moving away from each other at speeds proportional to their distances, suggesting that the universe is expanding. This expansion is a key prediction of the Big Bang theory, indicating that everything in the universe was once compacted into a single point of infinite density and temperature. These two groundbreaking discoveries, among others, have provided a solid foundation for the Big Bang theory, fundamentally changing our understanding of the universe's origins. The theory of cosmic inflation provides a fascinating explanation for the structure of the observable universe by suggesting a period of rapid exponential expansion immediately following the Big Bang. Proposed by physicist Alan Guth in the early 1980s, this theory posits that in the first fractions of a second after the universe's birth, it expanded at an astonishing rate, far faster than the speed of light, from a subatomic scale to a golf ball-sized universe. This rapid expansion smoothed out any initial irregularities and laid down the seeds for the large-scale structure of the universe we witness today. As the universe cooled and expanded at a slower rate following this inflationary period, regions of slightly higher density formed under the influence of gravity, eventually leading to the formation of galaxies, stars, and other cosmic structures. Inflation theory also explains why the universe appears to be the same in all directions, isotropic, and why it seems flat on large scales, solving several problems left unanswered by the Big Bang theory alone. This remarkable period of inflation is key to understanding why the universe has the structured but uniform appearance we can observe through our telescopes. While the Big Bang theory remains the most widely accepted explanation for the origins and evolution of the universe, there are still some unresolved issues and unanswered questions, suggesting it might be incomplete or need modifications. One of the primary challenges is the horizon problem, which questions how parts of the universe that are now billions of light years apart could have reached thermal equilibrium in the past, as observed in the uniform temperature of the cosmic microwave background radiation, despite not having had enough time to exchange information or energy. Another issue is the mystery of dark matter and dark energy. These invisible components are thought to make up about 95% of the universe's total mass energy content, yet they're not accounted for in the Big Bang theory. Furthermore, the theory does not provide insights into what preceded the singularity or how and why it occurred, leaving a gap in our understanding of the ultimate origins of the universe. These and other puzzles, such as the matter-antimatter asymmetry, suggest that our current model might require revision or supplementation from new physics, possibly from the realm of quantum mechanics or theories of gravity. Scientists continue to explore these unknowns, hoping to uncover a more complete picture of our cosmic origins. Dark matter is a mysterious and invisible form of matter that does not emit, absorb, or reflect light, making it completely undetectable by ordinary telescopes. Its presence, however, is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Dark matter is crucial to cosmology for several reasons. Firstly, it plays a key role in the formation and evolution of galaxies. The gravitational pull of dark matter helps to pull together the gas and dust needed to form galaxies and influences their rotational speeds. Observations, such as the rotation curves of galaxies, where stars at the outer edges rotate faster than can be accounted for by visible matter alone, suggest that a significant amount of unseen mass must be present. Secondly, dark matter contributes to about 85% of the total mass of the universe, making it a dominant component in the cosmic matter-energy content. This substantial presence affects the universe's rate of expansion and its overall structure, impacting the cosmic web of galaxies and the distribution of galaxy clusters. Understanding dark matter is therefore essential for a comprehensive understanding of the cosmos, from the smallest scales of galaxy formation to the vast cosmic architecture, and it continues to be a significant focus of modern astrophysics research. Dark energy, a mysterious force hypothesized to permeate all of space, plays a pivotal role in the expansion of the universe. Discovered through observations of distant supernovae in the late 1990s, scientists found that the universe was not only expanding, but doing so at an accelerated rate, contrary to the expectation that the universe's expansion should be slowing down due to gravitational attraction. Dark energy is thought to be responsible for this accelerated expansion. It acts as a sort of anti-gravity, pushing galaxies apart by stretching the fabric of space itself. This repulsive force accounts for approximately 68% of the total energy content of the universe. The influence of dark energy means that rather than slowing down, the universe's expansion is speeding up, a revelation that has profound implications for the ultimate fate of the cosmos. Understanding dark energy is one of the foremost challenges in modern cosmology, as it not only influences the large-scale structure and future of the universe, but also challenges our knowledge of physics, potentially requiring new theories to fully explain its properties and effects. The leading theories about the formation of galaxies and large-scale structures in the universe center around the cold dark matter, CDM model, with a cosmological constant, often referred to as LCDM. This model proposes that shortly after the Big Bang, the universe was filled with a nearly uniform hot plasma. Tiny fluctuations in density, possibly generated during the inflationary epoch, served as the seeds for structure formation. Dark matter, which does not interact with electromagnetic radiation, began to clump together under the influence of gravity, forming halos. These dark matter halos acted as gravitational wells that attracted baryonic matter, the material that makes up stars, planets, and living beings. As the universe cooled, gas within these halos condensed to form the first stars and galaxies. Over billions of years, these initial galaxies merged and grouped together, pulled by dark matter's gravitational forces, forming galaxy clusters, superclusters, and the vast cosmic web of filaments connecting areas of dense galaxy clusters and voids observed today. This hierarchical model of structure formation, where small objects form first and merge to create larger structures, is supported by a wide range of observations, including the cosmic microwave background, the distribution of galaxies in the universe, and simulations of galaxy formation and evolution. Another important aspect is the role of feedback mechanisms, such as supernova explosions and active galactic nuclei, which regulate star formation and the growth of galaxies by heating and expelling gas, preventing runaway star formation and resulting in the diverse types of galaxies observed. Through the LCDM framework and understanding these complex processes, cosmologists are able to explain the large-scale structure of the universe and the distribution and properties of galaxies within it. Yes, the movements of galaxies offer invaluable clues about the universe's overall structure and the underlying forces that govern it. One of the key insights comes from the observation of galaxies moving towards regions of higher gravitational potential known as the Great Attractor, suggesting that the distribution of mass in the universe is not uniform but clumpy, featuring massive clusters and superclusters as well as vast voids. Furthermore, the phenomenon of galaxies rotating faster than would be expected based on visible matter alone hints at the presence of dark matter, providing crucial evidence for its existence and helping to map its distribution. Another significant observation is related to the large-scale flow of galaxies, called peculiar velocities, which deviate from the universe's general expansion. These movements can be traced back to the early universe's density fluctuations, shedding light on the initial conditions following the Big Bang and the subsequent growth of cosmic structures through gravitational attraction. Galaxy surveys also reveal a filamentary structure, like a cosmic web, with galaxies congregated along filaments that intersect at massive cluster nodes, mapping out the universe's large-scale structure. Studying these patterns and movements not only informs us about the distribution of ordinary and dark matter, but also about the role of dark energy in accelerating the universe's expansion. By analyzing the dynamics and distribution of galaxies, cosmologists can refine their models of the universe's evolution, contributing to a deeper understanding of fundamental physics, the nature of dark matter and dark energy, and the initial conditions that have led to the universe as it is observed today. In the vast and intricate tapestry of modern cosmology, several pivotal questions remain unanswered, energizing the frontier of cosmic exploration and theory. Among the most profound is the nature of dark matter. Despite forming about 85% of the universe's total matter, dark matter eludes direct detection, known only by its gravitational effects. Unraveling what dark matter is made of remains a colossal challenge. Equally perplexing is the mystery of dark energy. This mysterious force, driving the accelerated expansion of the universe, constitutes about 68% of the universe's total energy content. Understanding why dark energy has the strength it does and how it fits into the broader framework of physics is a fundamental puzzle with profound implications for the fate of the universe. Another significant enigma is the question of the universe's exact rate of expansion, known as the Hubble constant. Discrepancies in measurements obtained by observing the early universe versus local, late-time observations suggest there may be new physics at play beyond our current understanding. Moreover, the question of why there is significantly more matter than antimatter, allowing the cosmos and everything in it to exist, challenges theoretical physics. The conditions following the Big Bang should have created matter and antimatter in equal amounts, leading to their mutual annihilation. Yet, the universe is dominated by matter, the reason for which remains elusive. The enigmatic inception of cosmic inflation, a period of rapid exponential expansion immediately following the Big Bang, puzzles cosmologists. What triggered this inflation? What stopped it? These are fundamental questions about the universe's birth and its earliest moments. Each of these questions represents a frontier in our cosmic journey, offering challenges to our understanding of the universe and inviting deeper inquiries into the nature of reality itself. Recent technological advancements have significantly expanded our view of the observable universe, pushing the boundaries of what we can see and understand about the cosmos. One of the most notable developments is the launch of the James Webb Space Telescope, JWST, in 2021. As the most powerful space telescope ever built, JWST is designed to observe the universe in the infrared spectrum, allowing it to peer through dust clouds and observe the light from the first galaxies that formed after the Big Bang, thereby providing insights into the early universe that were previously impossible. Another groundbreaking advancement is the detection of gravitational waves, first observed in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe, such as the merging of black holes. This new way of observing the universe has opened up a completely new field of astronomy, enabling researchers to study cosmic events that are invisible in electromagnetic radiation. Additionally, advancements in computational power and algorithms have revolutionized our ability to process vast amounts of data from telescopes and simulations. This has led to more precise measurements of the cosmic microwave background radiation, improved mapping of the large-scale structure of the universe, and more detailed simulations of galaxy formation and evolution. The Square Kilometre Array, SKA, planned to be the world's largest radio telescope, represents another technological leap forward. By combining signals from thousands of small antennas spread across large distances, the SKA aims to probe the early universe, test theories of gravity, and even search for extraterrestrial intelligence. These technological achievements, among others, are dramatically expanding our view of the universe, enabling discoveries that deepen our understanding of its origins, evolution, and the fundamental laws that govern it. Future telescopes and observatories hold the promise of revolutionizing our understanding of the cosmos, equipped with the potential to probe previously unreachable depths and aspects of the universe. One of the most anticipated projects is the Extremely Large Telescope, ELT, set to become the world's largest optical telescope upon completion. Its immense mirror will collect more light than any other optical telescope, allowing astronomers to directly image exoplanets, study the properties of their atmospheres, and investigate the universe's accelerating expansion in unprecedented detail. This could provide critical insights into the nature of dark energy and the potential for life on other planets. Additionally, the Square Kilometre Array, SKA, once operational, will have the sensitivity to detect extremely faint radio signals from the early universe, offering a new window into epochs shortly after the Big Bang that have remained elusive. It could unravel mysteries surrounding the era of reionization, the nature of dark matter, and the cosmic web structure of the universe. Furthermore, proposed missions to explore the gravitational wave universe more comprehensively, such as the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves from massive black hole mergers, stellar collapses, and possibly even remnants of gravitational waves from the Big Bang. This could open a new era of gravitational wave astronomy, providing insights into the most energetic processes in the universe and testing fundamental theories of physics. In the realm of observational cosmology, the next generation of satellites designed to measure the cosmic microwave background, CMB, with even greater precision, could sharpen our understanding of the early universe, inflation, and the contents of the universe at large scales. These technological marvels, together with advancements in data analysis, artificial intelligence, and theoretical physics, have the potential to unravel some of the deepest mysteries of the cosmos, from the nature of dark matter and dark energy to the origins of the universe and the laws that govern its evolution. By pushing the frontiers of observation and theory, future telescopes and observatories will not only enhance our understanding of the cosmos, but also our place within it. Observing the early universe presents astronomers with a myriad of formidable challenges, primarily due to the immense distances, faint signals, and the intervening cosmic matter that can obscure and distort observations. First and foremost, the light from the earliest stars and galaxies has traveled through the universe for billions of years, stretching to longer, redder wavelengths due to the expansion of the universe, a phenomenon known as redshift. This means that much of the light from the early universe now falls in the infrared spectrum, requiring specially equipped telescopes, such as the James Webb Space Telescope, to detect these faint signals. Another significant challenge is the cosmic microwave background radiation, CMB, which, while a treasure trove of information about the early universe, also acts as a veil, making it difficult to peer back to times before its emission, about 380,000 years after the Big Bang. This necessitates creative observational strategies and advanced theoretical models to infer the conditions of the very early universe indirectly. Further complicating matters, the light from distant objects must travel through the intergalactic medium, which can absorb and scatter it, altering the signal by the time it reaches Earth. This interstellar fog requires astronomers to carefully adjust their interpretations of the data to account for these effects. Moreover, the inherently faint nature of these ancient signals means that capturing them requires extremely sensitive instruments and often long observation times, making such endeavors resource-intensive. Competition for time on these facilities is fierce, and the development of new observatories capable of making these observations is both time-consuming and expensive. Finally, observing the early universe and interpreting the data demands sophisticated theoretical models and simulations to contextualize and understand the signals being detected. These models rely on our current understanding of physics, which may itself be challenged or refined by new observations, leading to a constantly evolving landscape of theory and observation in cosmology. Together, these challenges make observing the early universe a daunting yet exhilarating endeavor, pushing the boundaries of technology, theory, and human curiosity. Space missions have been instrumental in advancing our knowledge of the universe's composition, playing a pivotal role in unraveling the cosmos's intricate mysteries. By escaping the Earth's atmosphere, which absorbs and distorts electromagnetic radiation, space telescopes and probes can observe the universe across the entire electromagnetic spectrum, from gamma rays to radio waves. This capability allows astronomers to construct a more comprehensive and detailed picture of the universe's composition and its evolutionary processes. One of the most significant contributions comes from the cosmic microwave background, CMB observations, such as those by the Cosmic Background Explorer, COBA, and the Planck satellite. These missions have provided detailed measurements of the CMB's minute temperature fluctuations, offering critical insights into the universe's age, composition, and the distribution of matter and energy shortly after the Big Bang. This data underpins our understanding of the universe's overall composition, indicating that normal baryonic matter constitutes about 5%, dark matter about 25%, and dark energy about 70% of the total energy density of the universe. Space missions like the Hubble Space Telescope, HST, and the Gaia satellite have revolutionized our understanding of cosmic distances, the rate of the universe's expansion, and the distribution of matter across galaxies and galaxy clusters. Observations have detailed the large-scale structure of the universe and the role of dark matter in galaxy formation through its gravitational influence on visible matter. Moreover, missions designed to search for exoplanets, such as the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, contribute to our knowledge by determining the variety and distribution of planetary systems throughout the galaxy, offering insights into the potential for life-bearing planets and the processes of planetary formation. The detection of gravitational waves by facilities like LIGO on Earth and future space-based observatories like LISA will further elucidate the universe's composition by providing a new means of observing cataclysmic events, such as black hole mergers, that are invisible in electromagnetic radiation. By observing the universe from above the Earth's atmosphere and across all wavelengths of light, space missions have peeled back layers of cosmic mystery, revealing the fundamental nature of the cosmos and its myriad constituents. Computational simulations play an indispensable role in cosmological discoveries, serving as a bridge between theoretical models and observational data. They provide a powerful tool for testing hypotheses about the universe's origins, structure, and evolution, allowing scientists to explore the implications of physical theories and predict observable phenomena. One of the key areas where simulations have been pivotal is in the study of large-scale structure formation. By incorporating the laws of physics and initial conditions derived from observations of the cosmic microwave background into supercomputer simulations, cosmologists can simulate the evolution of the universe from shortly after the Big Bang to the present day. These simulations predict the formation of galaxies, galaxy clusters, and the intricate cosmic web of matter that fills the universe, matching remarkably well with observations from telescopes. Such simulations help to validate the current understanding of dark matter, dark energy, and the dynamics of gravitational collapse. Additionally, computational simulations are crucial for understanding galaxy formation and evolution. They enable scientists to dissect the processes of star formation, supernova feedback, and the interaction between galaxies and the intergalactic medium in great detail. By adjusting the parameters within these models, researchers can identify the factors that lead to the diverse range of galaxy types observed and understand the underlying mechanisms driving their formation and growth. In the realm of planetary science and astrobiology, simulations assist in predicting the conditions under which planets form and evolve, helping to identify potentially habitable exoplanets. Computational models of planetary climates and atmospheres provide insights into the conditions necessary for life and guide observational efforts to search for biosignatures. Moreover, the detection of gravitational waves has opened a new frontier for simulations, allowing researchers to model cataclysmic events such as black hole and neutron star mergers with unprecedented precision. These models are essential for interpreting the signals detected by observatories like LIGO and Virgo, furthering our understanding of the extreme conditions in the universe. Technological innovations in observational astronomy are not only expanding our understanding of the universe, but are also revolutionizing the methods by which we explore cosmic phenomena. One such transformative technology is adaptive optics, which significantly improves the quality of images obtained from ground-based telescopes. By compensating for the distortions introduced by Earth's atmosphere in real time, adaptive optics allows telescopes like the ELT to achieve image clarity that rivals or surpasses that of space telescopes, enabling more detailed studies of astronomical objects from the ground. As we project into the future, the development of quantum sensors promises to elevate astronomical measurements to new heights. These sensors could dramatically enhance the sensitivity and resolution of astronomical instruments, allowing for the detection of signals that are currently too faint or too complex to decode. Quantum-enhanced technologies are expected to improve the measurement of cosmic gravitational fields, potentially revolutionizing our ability to test the limits of general relativity and probe the dark components of the universe. Another forward-looking technology involves the integration of artificial intelligence, AI, with astronomical data processing. AI and machine learning algorithms are proving indispensable in handling the deluge of data from advanced observatories and telescopes. These technologies not only speed up data analysis, but also improve the accuracy of object detection and classification, opening up new possibilities for automated exploration of the universe. Moreover, advancements in space technology continue to provide vital platforms for observational astronomy. Future missions, potentially involving spacecraft equipped with advanced propulsion technologies, could venture further into space to deploy telescopes and probes in locations unhindered by the constraints of Earth-based observations. For example, missions to the far side of the Moon or to stable Lagrangian points could establish new observational posts that are shielded from Earth's radiative and radio noise, providing clearer views of the cosmic horizon. The synergy between multi-messenger astronomy, which combines data from electromagnetic waves, gravitational waves, neutrinos and cosmic rays, and new observational technologies, will likely be pivotal. This holistic approach could unveil the processes behind the most extreme and mysterious events in the universe, such as gamma-ray bursts, neutron star collisions, and black hole mergers. Overall, computational simulations are an essential tool in the cosmologist's toolkit, offering a lens through which the past, present, and future of the universe can be explored and understood. Through the iterative process of model refinement informed by observational data, simulations continue to advance the frontiers of cosmological knowledge. Discoveries about the universe have profoundly challenged and expanded philosophical ideas concerning our place in the cosmos. Historically, humans have often viewed themselves as central to the universe, a concept known as the geocentric model. However, astronomical discoveries have systematically dismantled this view, starting with the Copernican revolution, which posited that Earth orbits the Sun, not the other way around. This was the beginning of a series of revelations that relegated Earth from the center of the universe to merely one planet among billions in a vast and expanding cosmos. The discovery of the vast scale of the universe, with billions of galaxies each containing billions of stars, many with their planetary systems, underscores the humbling realization of our insignificance in terms of space. The realization that the observable universe is about 93 billion light-years in diameter and possibly part of a much larger or even infinite cosmos has profound implications for our understanding of our place in the universe. Furthermore, the discovery of the laws of physics that govern the universe, from subatomic particles to galactic clusters, suggests that the universe operates according to principles and forces that are indifferent to human existence. This challenges anthropocentric views and raises philosophical questions about meaning, purpose, and the nature of existence. The revelation of cosmic timescales, where the universe is approximately 13.8 billion years old, and Earth's formation and the evolution of life represent a mere fraction of cosmic history, further challenges human perspectives on time and our significance within the grand narrative of the universe. Moreover, the discovery of potentially habitable exoplanets and the ongoing search for extraterrestrial life confront philosophical and ethical questions about humanity's uniqueness and the possibility of other intelligent beings in the cosmos. Finally, ideas like the multiverse theory, suggesting our universe might be just one among many, push the boundaries of how we conceptualize reality and our place within it, confronting us with the possibility that our universe is not the only stage upon which the drama of existence unfolds. These cosmological discoveries invite a re-evaluation of human significance in a vast, ancient, and perhaps infinitely diverse cosmos, urging a philosophical shift from an anthropocentric to a more cosmic-centric perspective. They inspire awe and wonder, but also a profound humility as we wrestle with the implications of our cosmic context and the quest for understanding our place within it. The potential discovery of life beyond Earth could have profound societal impacts, reshaping worldviews, philosophical and religious frameworks, as well as scientific and cultural narratives on a global scale. The realization that we are not alone in the universe would likely spur a profound collective reflection on human identity, unity, and our place in the cosmos, potentially fostering a more global perspective that transcends nationalistic and parochial concerns. Scientifically, the discovery would inaugurate a new era of biological research, expanding the science of biology from an Earth-centric to a universal discipline. This could lead to a significant shift in our understanding of life's origins, evolution, and the conditions necessary for its emergence. It would also likely invigorate public and private interest and investment in space exploration and research, aiming to learn more about our cosmic neighbors. Philosophically and theologically, the existence of extraterrestrial life could challenge traditional belief systems and interpretations of human uniqueness and the notion of Earth as the center of life in the universe. Different religions and belief systems might need to reinterpret, adapt, or reaffirm their teachings in light of new findings. This could lead to a wide range of reactions, from existential questioning to a reaffirmation of faith and interfaith, dialogues about life's ultimate questions. Ethically, The discovery necessitates developing frameworks for protecting potential extraterrestrial ecosystems from harm, which could foster a broader sense of responsibility toward the stewardship of life in the cosmos. This could influence environmental and conservation efforts on Earth, highlighting the fragility and rarity of life. Socially, the discovery could unite humanity in curiosity and wonder, but it could also create divisions based on differing interpretations of the significance of such a discovery. Handling the dissemination of information will be crucial to avoid panic, misinformation, and sensationalism, requiring a carefully thought-out communication strategy that involves scientific, governmental, and community leaders worldwide. The potential discovery of life beyond Earth invites us to envision a future where humanity is part of a broader community of life in the cosmos. It beckons us to contemplate not only our scientific achievements, but also the philosophical, ethical, and societal implications of becoming a spacefaring civilization that knows it is not alone in the universe. Exploring the universe serves as a powerful catalyst for technological innovation on Earth, weaving a tapestry of creativity and problem-solving that benefits humankind in countless ways. The daunting challenges of space exploration push scientists and engineers to their limits, inspiring the development of new technologies or the improvement of existing ones. For instance, the need for compact, efficient power sources for long-duration space missions has accelerated advancements in solar panel technology, which now light up homes and power industries on Earth. Similarly, the quest to understand Mars's atmosphere led to the creation of sophisticated sensors that are now used to monitor air quality and detect pollutants with unprecedented precision. Moreover, the extreme conditions of space demand extraordinary materials, leading to innovations such as memory foam and scratch-resistant lenses that have found widespread use in everyday life. Thus, the exploration of the cosmos not only expands our understanding of the universe, but also sparks technological progress that enhances our quality of life on Earth. Cultural perspectives play a significant role in shaping our understanding of the universe, coloring the way we interpret celestial phenomena and the cosmos at large. Throughout history, different cultures have looked up at the same sky, but have woven unique narratives and explanations around the stars, planets, and the cosmos, each reflective of their distinct beliefs, values, and social structures. For example, ancient Greek mythology saw constellations as representations of their gods and heroes, deeply intertwining their astronomical observations with their mythological tales. In contrast, Native American tribes often viewed celestial bodies as part of a larger, interconnected natural world, with stories that emphasized harmony and balance within the universe. These cultural perspectives influence not only historical interpretations, but also modern scientific inquiry. The names of celestial objects, the prioritization of certain research directions over others, and even the ways in which scientific findings are communicated can all reflect underlying cultural biases or viewpoints. Acknowledging this influence can enrich our understanding of the cosmos by encouraging a more holistic approach that incorporates diverse cultural insights and perspectives, thereby broadening the scope of cosmic inquiry beyond purely scientific dimensions. The search for extraterrestrial intelligence, SETI, raises profound ethical considerations, probing not only our technological capabilities, but also our philosophical and moral frameworks. One of the primary concerns is the question of initiating contact. The debate revolves around whether humanity should actively send messages into space to announce our presence, or whether we should listen quietly, wary of the unknown intentions or capabilities of potential extraterrestrial civilizations. This dilemma underscores the importance of a cautious approach that weighs the desire for knowledge against the potential risks of revealing our existence to potentially more advanced beings. Furthermore, there's the matter of representing Earth as a unified planet without a single governing body or shared values. Deciding who gets to speak for humanity and what messages should be sent encapsulates complex ethical questions about inclusivity, representation, and authority. Additionally, the search for extraterrestrial intelligence invites reflection on our treatment of other forms of life and intelligence here on Earth. It challenges us to consider whether our actions towards other species and towards different human cultures reflect the kind of species we aspire to present to the cosmos. This introspection could guide us towards more ethical behaviors within our own planet, emphasizing respect, understanding, and protection for all forms of life. There's an ethical responsibility towards safeguarding sensitive information. Discovering indisputable evidence of extraterrestrial intelligence would be a transformative event for humanity, one that could have profound effects on our societies, religions, and individual worldviews. Managing such information with care, ensuring it's authentic and responsibly shared, is crucial to prevent misinformation, panic, or unwarranted fear. The revelation that the universe is not only vaster, but also far more complex than previously understood, underscores the need for a philosophical realignment in how humanity perceives itself within the cosmic order. This expanding cosmic perspective necessitates a shift from a predominantly anthropocentric worldview to a more universe-centric philosophy, compelling us to rethink our roles and the meaning of human actions in a broader, more interconnected cosmos. The implications of such discoveries extend into the realm of existential philosophy, where thinkers have long grappled with the concept of existential absurdity, the idea that life might inherently lack meaning in a vast, indifferent universe. These modern cosmological discoveries, revealing a universe filled with countless galaxies and potentially habitable planets, may seem to underscore this notion of absurdity. However, they also open up new avenues for finding meaning through a revised understanding of our relationship with the universe. By recognizing our small but unique place in the cosmos, we can redefine our pursuit of meaning as a quest not centered on dominance or survival, but on harmony and understanding within the cosmic framework. Ethically, the vastness of the universe and the potential multiplicity of sentient life forms challenge our Earth-centric moral frameworks. It prompts a reconsideration of our ethical obligations not only towards other humans, but towards all forms of life and the environments they inhabit, potentially across the universe. This ethical expansion could lead to what some philosophers term cosmic ethics, a form of ethical theory that includes care for the cosmos as a whole, advocating for the stewardship of not just earthly environments, but also cosmic ones, especially in light of activities like space mining and interplanetary contamination. Socially, the potential for multiple diverse civilizations within the universe suggests a need for an interstellar version of multiculturalism. If and when humanity encounters extraterrestrial intelligence, we will face profound questions about tolerance, communication, and the sharing of resources and space. These encounters could serve as a mirror, reflecting our own societal values and prejudices and challenging us to transcend them. Philosophically, the concept of the multiverse reinvigorates classic debates concerning determinism and free will. If multiple universes exist, each potentially with its own set of physical laws and constants, the philosophical implications regarding fate and predetermination could be profound. This could lead to a revitalized interest in modal realism, the idea that all possible worlds are as real as the actual world, in philosophical circles, potentially altering our perception of reality and our decisions within it. Culturally, these cosmological shifts influence not only scientific and philosophical thought, but also the narrative arts, inspiring literature, film, and art that explore these themes. The idea of a multiverse has already permeated popular culture, prompting reflection on themes of identity, alterity, and the very nature of reality. This cultural digestion of cosmological concepts plays a crucial role in shaping public understanding and acceptance of these complex ideas. The philosophical and societal implications of our expanding understanding of the universe are profound and pervasive, urging a holistic reconsideration of many foundational aspects of human thought and culture. As we navigate the vast unknowns of our universe, these ethical considerations in the search for extraterrestrial intelligence compel us to reflect on not only who we are, but also who we aspire to be. As scientists aim to peel back the layers of mystery surrounding the observable universe, they are charting ambitious next steps that promise to deepen our understanding of the cosmos. One pivotal approach is the advancement and deployment of more powerful telescopes, both ground-based and in space. Instruments like the James Webb Space Telescope, set to succeed the Hubble Space Telescope, are designed to observe the universe in unprecedented detail, peering back in time to the universe's infancy and potentially uncovering clues about what lies beyond the observable limits. Concurrently, researchers are delving into the cosmic microwave background radiation, the afterglow of the Big Bang, using increasingly sensitive detectors. This radiation offers a glimpse into the earliest moments of the universe, potentially revealing insights about its overall structure and the mechanisms driving its expansion. Scientists hope that studying the subtleties in this cosmic backdrop might hint at the existence of realms beyond our observable universe. In the realm of theoretical physics, efforts are underway to unite the theories of quantum mechanics and general relativity, which could lead to the development of a theory of quantum gravity. Such a theoretical framework might provide the tools necessary to conceptualize and investigate the properties of the universe beyond the reach of our current observational technologies. Furthermore, initiatives in the field of computational astrophysics are using advanced simulations to model the universe's evolution under various scenarios, some of which hypothesize conditions that could exist beyond the observable cosmos. These simulations help scientists to understand how different theories of the universe's structure might manifest in observable phenomena. These interdisciplinary and innovative strides in exploring beyond the observable universe are not merely expanding our cosmic horizons, they are also compelling us to rethink fundamental questions about the nature of reality, the origins of the universe, and our place within the vast cosmic expanse. The laws of physics as we know them are a foundation upon which our understanding of the universe is built, yet they are not immutable. As new discoveries about the universe emerge, these laws may undergo profound transformations, challenging our existing frameworks and propelling us into new realms of thought. Historically, shifts in our understanding of the cosmos have often led to revisions in the laws of physics. For instance, the realization that Earth was not the center of the universe, but rather orbited the Sun, necessitated a re-evaluation of celestial mechanics, culminating in Newton's laws of motion and universal gravitation. In contemporary times, the discovery of dark matter and dark energy has highlighted the limitations of our current understanding of gravity and the large-scale structure of the universe. Such enigmas challenge the completeness of general relativity and suggest that our grasp of gravitational forces might need refinement to accommodate these dark constituents. Similarly, the peculiar behaviors observed at quantum scales, where particles seem to exist in multiple states simultaneously, demand a reconciliation with the deterministic predictions of classical physics, hinting at a yet undiscovered theory that can unify the quantum and cosmic scales. As we push the boundaries of our knowledge, especially with endeavors aimed at understanding the conditions during the universe's first moments or the intricacies of black hole singularities, we are likely to uncover phenomena that do not fit within our current theoretical framework. Such discoveries could necessitate the formulation of new laws or the modification of existing ones, incorporating principles that might seem alien to our current understanding. The evolution of the laws of physics with new discoveries is a testament to the dynamic nature of scientific inquiry. It underscores the fact that our current knowledge is but a snapshot in the ongoing journey of understanding, open to refinement and revolution as we uncover more about the universe's mysteries. This ever-evolving pursuit not only enriches our comprehension of the cosmos, but also continually reshapes the science with which we seek to understand the very fabric of reality. The theoretical limits of human exploration in space are defined by a combination of physical, technological, and biological constraints, each imposing significant challenges to the expansion of human presence beyond our immediate cosmic neighborhood. Physically, the vast distances between celestial bodies present a formidable barrier. For instance, even light, the fastest known entity in the universe, takes about 4 years to travel from the nearest star to Earth. With current propulsion technologies, a journey to even the closest star systems would take thousands of years, making interstellar travel impractical within a human lifespan. On a technological level, developing spacecraft capable of sustaining human life for the duration of such extended missions involves overcoming immense obstacles, from ensuring reliable life support systems to shielding against cosmic radiation. While advancements in propulsion systems, such as the concept of nuclear or antimatter propulsion, could theoretically reduce travel times significantly, these technologies are in their infancy and come with their own set of challenges. Biologically, the human body is not well suited to prolonged periods in space. The microgravity environment has detrimental effects on muscle mass, bone density, and overall health. Additionally, exposure to cosmic radiation outside the protective embrace of Earth's magnetic field poses a serious risk of radiation sickness and increased cancer rates among astronauts. Psychological factors, such as the isolation and confinement of long-duration spaceflight, also pose significant challenges to the mental well-being of crew members. Despite these daunting challenges, ongoing research and development aim to extend the reach of human exploration. Innovations in propulsion technologies, life support systems, and radiation shielding combined with a deeper understanding of human health in space, are gradually pushing the boundaries of what's possible. While theoretical limits exist based on our current scientific understanding and technological capabilities, history has shown that today's theoretical limits might become tomorrow's starting points as we continually advance our knowledge and technology. Understanding the universe beyond our observable limits holds immense potential to reshape the future of humanity in profound ways. Venturing into these unknown realms can revolutionize our foundational knowledge of physics, cosmology, and perhaps even the origins and fate of the cosmos itself. It would compel us to refine or even redefine our understanding of the fundamental forces and particles that constitute the fabric of the universe, possibly uncovering new physics that could lead to groundbreaking technologies. These advancements could facilitate novel forms of energy production, space travel, and communication, potentially transforming societal structures, economies, and daily life on Earth. For instance, harnessing energy or technologies inspired by cosmological phenomena could propel us towards a future of sustainable and abundant energy, addressing some of the most pressing environmental challenges of our time. Moreover, a deeper comprehension of the cosmos might offer insights into the likelihood of extraterrestrial life and the nature of intelligence in the universe, reshaping our perception of our place in the cosmic order. This could have significant cultural and philosophical implications, fostering a sense of cosmic perspective and unity that encourages global collaboration and harmony. In a broader sense, expanding our cosmic horizons can act as a catalyst for addressing existential threats. Understanding potential cosmic hazards such as asteroid impacts or gamma-ray bursts with greater clarity could spur the development of defensive technologies to protect humanity and our planetary home. Ultimately, pushing the boundaries of our cosmic knowledge enkindles the human spirit of exploration and discovery, driving advancements in science, technology, and thought that benefit humanity in myriad ways. It underscores our relentless pursuit of understanding, not just to unravel the mysteries of the cosmos, but to elevate our species to new heights of existence and potential. Scientists are delving into a range of speculative theories that push the boundaries of our understanding of the universe. One prominent area of exploration is the concept of the multiverse, suggesting that our universe might be just one of numerous distinct universes within a vast, possibly infinite, cosmic expanse. This theory, which emerges from the fields of quantum mechanics and inflationary cosmology, proposes that these universes may have different physical laws or constants, providing a fertile ground for understanding the fundamental parameters of our own universe. Another speculative theory gaining traction is string theory, which posits that the most fundamental components of the universe are not point particles, but rather tiny vibrating strings. String theory aims to unify general relativity and quantum mechanics, offering a framework that could explain everything from the fabric of space-time to the nature of black holes. Within this theory lies the intriguing possibility of extra dimensions beyond the three spatial dimensions and one time dimension we experience daily. Scientists are also exploring the notion of dark matter and dark energy, constituting about 95% of the universe's total mass energy content, yet remaining deeply mysterious. Theories abound regarding the true nature of dark matter, from weakly interacting massive particles, WIMPs, to axions, each suggesting different ways these elusive substances might interact with the observable matter. Similarly, the enigmatic force of dark energy, which drives the universe's accelerated expansion, challenges our understanding of gravity and the cosmos's future. Additionally, the holographic principle has emerged as a fascinating speculative idea, suggesting that all the information contained within a volume of space can be described by information on the boundary of that space. This principle, inspired by black hole thermodynamics, hints at a universe where our perceptions of 3 dimensions may be a projection of information encoded on a distant, 2-dimensional surface. These speculative theories are at the frontier of scientific exploration, forging paths into uncharted realms of the cosmos. Despite their speculative nature, they are grounded in rigorous mathematical frameworks and are gradually being tested through observations and experiments. They represent the cutting edge of human curiosity and ingenuity, driving forward our quest to uncover the deepest truths of the universe. As we look to the future of cosmology and the exploration of the universe, the intersection of emerging technologies and groundbreaking theories promises to propel our understanding into new realms. The advancements in observational tools and theoretical frameworks are not merely extending our reach into the cosmos, but are also challenging our most fundamental notions about the nature of reality and the fabric of space-time. The deployment of next-generation telescopes such as the James Webb Space Telescope, JWST, and the planned construction of the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, marks a significant leap forward in our capability to observe the universe. These instruments will allow us to see farther and with greater clarity than ever before, potentially uncovering phenomena that challenge existing cosmological theories and extend our visual reach to the very edges of the observable universe and beyond. Simultaneously, advancements in sensor technology and computational capacities are enabling us to analyze the cosmic microwave background radiation with unprecedented precision. This analysis could reveal subtle fingerprints of the pre-inflation universe, offering clues about the mechanisms driving the universe's expansion and possibly about dimensions and realms beyond our standard 4-dimensional space-time continuum. On the theoretical front, efforts to reconcile the theories of quantum mechanics and general relativity into a unified theory of quantum gravity are gaining momentum. This endeavor could fundamentally alter our understanding of gravitational forces across the scales, from the tiniest particles to the most massive black holes and the overall architecture of the universe itself. A successful theory of quantum gravity might also provide the necessary theoretical tools to penetrate the veil of the cosmic horizon, offering insights into what may lie beyond the observable limits. Moreover, the utilization of computational astrophysics to simulate the universe provides a powerful tool for testing the implications of different theoretical models. These simulations help cosmologists to predict how universes under various physical laws might evolve, aiding in the refinement of theories such as string theory, the holographic principle, and theories surrounding dark matter and dark energy. These scientific advances are deeply interdisciplinary, drawing from fields such as particle physics, quantum theory, relativity, and information theory. They not only enhance our understanding of the cosmos, but also have the potential to lead to revolutionary technologies in materials, science, quantum computing, and energy production, echoing the transformative impact of space research on satellite communications and GPS technologies. The philosophical and ethical dimensions of these discoveries are profound. As we uncover more about the universe, we inevitably confront questions about the origins of life, the nature of consciousness, and the potential for other intelligent beings. These questions encourage a shift from a human-centric worldview to a broader, more inclusive cosmic perspective that respects and values life in all its potential forms. As we stand on the brink of these transformative discoveries, a unified approach that integrates technological innovation with theoretical exploration will be crucial. Collaboration across disciplines, institutions, and nations will likely be necessary to tackle the technical challenges and to interpret the complex data that these new tools will generate. The future of space exploration and cosmological theory holds not only the promise of answering some of the most fundamental questions about the universe, but also the potential for unprecedented technological and philosophical growth. As we peer deeper into the cosmos, we are likely not only to discover new realms, but also to redefine our place within the universe. A journey that is as much about exploring the cosmos outwardly as it is about understanding our inner capacities and the underlying truths of our existence. These endeavors remind us that the pursuit of knowledge about the universe is ultimately a reflection of our quest for understanding ourselves and our place in the broader cosmic tapestry. Let us know your thoughts in the comments below. Thanks for watching.